let's look at the integral of secant cubed x dx. So again, we're dealing with secants, and we know the integral of secant squared, so we might be thinking back to our basics. And so these will probably play a role somehow. We just want to keep track of them. The tangent goes to secant squared, secant goes to secant tan as far as derivatives are concerned, and then just going in the other direction, we have the integral of secant squared handy that goes to tan x, and then secant and tan goes to secant. Now, if we go through the thought process of what are we trying to do, normally we try to create a u and a du. So we say, okay, strip out a secant squared, we've been in the habit of that, and save that as your du if you want, since you have a secant cubed x. And maybe change the rest into tangents. That's usually what we do. We pull out a secant squared by itself. And if we try that here, notice we go, okay, I'm going to strip out a secant squared x dx like I normally do when I save it for my du, because obviously I don't have a tangent here to strip out a secant x tan x to save for my du. And then when we do that, we change the rest, whatever's left over, to tangent, so we can make use of this guy. Strip out a secant squared x, change everybody left over into tangents. But we can do that if we have squares involved and we use the Pythagorean identities. Notice in this case, I don't have any squares involved for me to be able to use the Pythagorean identity here and then change everything to tangents. So that option of stripping it out and creating a u and a du actually won't work here. You're sort of stuck. But you do notice that we know the integral of this guy right here. It's fairly easy. And we also know the derivative of this guy. It's fairly easy. It's here. And we do know that we're looking at a product. And if you remember from before, if you have a product of two things where you know the integral of one fairly easily and the derivative of the other fairly easily, then you're going to make use of integration by parts. And normally we use LIPIT, logs, inverses, polynomials, exponentials, then trig functions for our u. Which one do we call our u? LIPIT is what we've been using in class so far. But here everything seems to be trig. So might as well maybe put this one, since we know its derivative is easy to do, and we know that that integral is easy to do. So we'll say u is secant x, dv is your leftover business. And then if I know u, I know du is secant x tan x dx. And if I know my dv, my v from here is tan x. So let's see what's going to happen when we do our uv minus v du business. Almost looks like a u, I mean a v du. So uv, let's put that in, uv will give me secant x tan x minus integral of v du. So v is tan x, and du is secant x tan x dx. Okay, so what we have so far is secant x tan x, that's taken care of. And over here I got two tangents, that's tangent squared x, secant x dx, which makes me happy for now because I have a combination of those two guys, and maybe these guys over here will help me out in figuring that out. Now, if I look at this piece, because now this is where I want to focus, if I can just integrate that, then I'm pretty much done. Now you have a combination of tangents and secants, and remember, you want to strip out your du and pull it on the side and see what happens. So if I want to strip out a du, I don't have a secant squared, so I can't pull out a secant squared and change things to tangents. Well, my other option is, what if I pull out a secant x tan x on the side and then use this guy? But if I pull out a secant x tan x and I put it on the side, I will only be left with one tangent x. So though it seems like I'm going backwards into this step, this is just for analysis. I pulled out secant x tan x to save it as my du. And then this, if I'm saving that as my du, everybody else over here better be in terms of secants. But this is a tangent x, it's not a tangent squared x, so I can't use this guy to change it into secants as I would wish. So stripping out a secant x tan x for my du doesn't help me in this case, and I can't strip out a secant squared in this case because I don't have a secant squared. So I'm kind of stuck again. These guys they don't help me out. So the only other option I have is, well, let me see what I can do with tangent squared x using this identity. Let's just play around with that and see what'll happen. So secant x tan x minus this guy tan squared x is going to be, move the 1 over, so it'll be secant squared x minus 1 secant x dx. And you might think, well, how does that help? Well, it helps a little for right now, because if I distribute that guy in, I get what we used to call good news when we were looking at integration by parts type 2. Remember what type 2 said? It's good news if you see your original integral appearing again. And it looks like this very original integral I started with is sort of reappearing here with some other business. So semi-good news, let's carry on. I'm going to have secant x tan x minus, split this up, it's a different, secant cube x, don't forget your dx, this dx applies to everything in the sum and the difference, minus out in the front, minus in the middle, distributing will give me a plus secant x dx. Okay? So all of this business, remember, is equivalent to what I had started trying to analyze. This was my original problem, original integral. And this is where I'm at so far. And we did this guy earlier, and we said that's just going to be ln of secant x plus tan x. Remember, it involved that little trick of multiplying top and bottom by an equivalent looking one. So here's where we're at. We're at a place where we have one guy here that are identical, both of them, same. Let's get them on the same side. Get my x. And when I get them on the same side, I have two of these guys equals, this is gone, no more integrals left on the right side. Good news. And I've pretty much gotten there. All I have to do is divide everything by 2, and integral of secant cube x dx is actually a half secant x tan x plus a half ln secant x plus tan x plus c. So what started out as being a trig integral, and we tried to strip out whatever we could using these guys and create a u and a du. It didn't work out for us. Instead, we noticed we know the derivative of one fairly easily. We know the integral of the other fairly easily. Let's try by parts. And in doing by parts, it wasn't a type 1, it turned out to be a type 2 because we saw the original integral repeat again.